Hello everyone. Today we are going to see the one most important derivation of first PUC, obtain expression for final velocities of two particles undergoing completely elastic collision in one dimension. So what is collision? Collision is a physical striking between the two bodies, right? Then what is elastic collision? Elastic collision in which the momentum and the kinetic energy of the system are the conserved of the colliding bodies. Then what is one dimensional? If the initial velocities and the final velocities of two colliding body are along the same straight line, then it is called as one dimensional or head-on collision. So let us consider two bodies A and B of masses m1 and m2 moving with initial velocities of A it is u1 and of B it is u2. This is the scenario before the collision. Okay, so consider two bodies, they are moving with initial velocities. Okay, so this is before the collision. After the collision, what happens is body A moves with initial final velocity v1 and body B moves with final velocity v2. That is after the collision. Now, as a suggesting scenario, consider two bodies A and B of masses m1 and m2 respectively, moving in a straight line as it is one dimensional collision with initial velocities u1 and u2 of bodies A and B, and let v1 and v2 be their final velocities after collision. Okay, so this is what we should consider first. So let us assume that m1 mass is greater than m2 mass because it helps during the collision. Okay, now as we know that in elastic collision momentum and kinetic energy is conserved, right? So we know the law of conservation of momentum from fourth chapter, that is laws of motion, right? Yeah, from that we can derive the law of conservation of momentum for these bodies with taking masses of two bodies m1 and m2 and initial velocities u1 and u2. Okay, so from that we can say that total momentum of the system before collision is equal to total momentum of the system after collision. So we can write it as momentum of the system before collision is equal to momentum of the system after collision, right? So momentum of the system before collision, what is momentum formula? Mass into velocity. So we have two velocities u1 and u2. So what does that say? That law of conservation of momentum, it's the same. m1 u1, that's initial, m2 u2 is equal to m1 v1, that's final, and m2 v2 is the second body, right? So this we will keep it as equation 1. Okay, so for simplification we can just take m1 and m2 common, right? So here we can take m1 common, so bringing m1 v1 to left hand side, so what it becomes, m1 u1 minus m1 v1. So I will take m1 common and I will get m1 into u1 minus v1. Okay, in the right hand side we can see that m2 v2 is as it is, m2 u2 will go to right hand side and it will become minus, right? So m2 v2 minus m2 u2, which I will take m2 as common and I will write v2 minus u2. Okay, this is equation 2. We also know that kinetic energy is conserved in elastic collision. So from the law of conservation of energy, so we can write kinetic energy of the system before collision is equal to kinetic energy of the system after collision. So what is difference in this? So in momentum m1 u1, right? So here what u2, multiply by half and make u1 square. Continue with all those four terms. Okay, so you will get the kinetic energies of the two bodies before collision and after collision. Okay, so as it is kinetic energy, I have written it half m1 u1 square plus half m2 u2 square is equal to half m1 v1 square plus half m2 v2 square. Okay, you may not, it is not visible v2 square, but I have written there. Okay, it's my fault. Okay, so half m1 u1 square plus half m2 u2 square. See, kinetic energy in the sense half mv square, right? So there is mass, there is velocity, so you can write it. Later, take half common. Okay, take half common and half will get cancelled, so you will get that remaining equation. Okay, that momentum equation, same as what you did in first case. Do it here, take the masses common and subtract the velocities. So I have written the two equations, 3 and 2, one below the other. So above equation is equation number 3 and below is equation number 2. So we know the formula, right? A square minus b square. What is it? A plus b into a minus b, right? So we can expand u1 square minus v1 square as this formula. So u1 square minus v1 square, the v2 square minus u2 square. What it will become? u1 plus v1 into u1 minus v1. Here v2 plus u2, v2 minus u2. Here we can cancel out m1, right? And u1 minus v1, u1 minus v1. Yeah, in here also same. In RHS also m2 can be cancelled. v2 minus v2, v2 minus v2 can be cancelled, right? So what is remained? u1 plus v1 is equal to v2 plus u2, right? So in this we want v1. So v1 is equal to v2 plus u2. So u1 comes to right hand side, so it becomes minus u1, right? We will name it as equation number 4, and similar with v2, which is u1 plus v1 minus u2. Okay, equation number 5. Now substituting equation number 4 in equation number 1, okay, which is m1 u1 plus m2 u2, which is equal to m1 v1 plus m2 v2. Correct? Here what we are going to substitute? v1. So v1 is equal to v2 plus u2 minus u1 plus m2 v2, right? And from there multiply m1 with the terms inside the bracket. Then later take m1 u1 as common and u2 as common with m2 minus m1 in right hand side, v2 m1 plus m2, okay, v2 as common. By substituting equation 4 in 1, we get v2. Similarly, by substituting equation 5 in 1, we get v1. Okay, hence we obtain final velocities of two particles undergoing elastic collision in one dimension. Okay, so in the same way you can find for inelastic collision also. So I hope you liked this video, understood this concept very well. Thanks for watching. Keep supporting.